Okay, so today we have a real lot to cover actually, so let's go ahead. So we're talking about general purpose digital input and LCD interfacing, and that's something that you will be starting with today. So first a little review. So when we talk about ports, right, they're labeled B, C and D on our Atmega processor. Then you can set them up for reading and writing, and the way to do this is to use this directional register and set the bits accordingly to which pins on that port, B, C or D for X over here, will correspond to an output or an input. And the port X over here is an I/O register, so you can write a bit to the port and that will set the output on that pin to a high or low voltage if the corresponding DDR-X is set to 1, indicating that you indeed want to use the pin as an output. Now the pin register over here only contains inputs, and you can only read that particular register. Now what you could do is you could, for example, set a port to output, and then you may set the actual bits that you want to write to those pins, but you could read the pin register and you will notice that this one will have the exact same value as what you had given in the port register. Okay, so how does this all work? So first of all, I hope you have checked this header file maybe after last class, but you will see all these definitions over here. So this is a register truly linked to what the hardware sees as input, but over here we see all these constants, right? That's what I like to stress once more, that pin B0 is nothing but the actual integer 0, pin B1 is just equal to the integer 1, and so forth. And we use that just to mask pin B by, for example, looking at pin 3, shifting over 3 positions to the left, and then figuring out through an AND operation on the whole register pin B what the output is, will teach you whether that third bit is actually a 1 or a 0. And you can also use that for clearing, right? Yeah, you can do that as well. Now, so here you see all these different tables. So I would really encourage you to have a look at the header file and see what is defined. Alright, so now let's move ahead. So again, I like to stress once more, if you're going to read the pin register, we just define some kind of variable, for example character here. And suppose the pin B register has this particular bit value, so 8 bits, 10, 10, 10, 10, then the register value would be equal to this. Now we create a mask, for example the 7-bit, which 7 is a constant, we replace it by pin B7, and in this way we can now write something like this in an if statement where we take the actual register and AND it with this particular one left shifted over pin B7 positions, which is this particular mask, and that will teach us what that output pin actually has, the 7 pin. Alright, now let's go on with some new stuff. So first of all, if you are looking at a button push, then what you will see is actually what we call a tri-state buffer. So I'll explain it in a moment. But let's first talk about what actually happens. So if you just have a naive kind of button circuit and you press it, you will actually notice that this button switch dangles in the air a little bit, and really depending on the frequency of local radio stations and so on, you will see high or low voltages. So it's not immediately clear what that output is, and it's of course rapidly will stabilize, but it's unreliable to begin with. So you will see, if you use, say, a pin programmed as an input coming from that switch, then you will see rising and falling edges maybe pretty fast in a very short time span appearing on that pin. So now what does that mean? Does that mean that the button actually get pushed or not pushed because you go up and down with that with the high and low voltage? So a good thing to do is to use a pull-up register, and so that if the switch is open, then effectively that filters the voltage, right? So that so that you know that you sort of filter out that noise. So all right, so that is what you would do. Now, implicitly, this pull-up resistor is actually implemented by setting the output of the pin to high as a result of programming the port. So that's kind of interesting. So you can therefore make your input more reliable by, even though you don't use the port because you're not using the pin as an output, but by setting the port in that particular position to a 1, you make it more reliable. Alright, so what's a tri-state buffer then? Well, something as simple as this. It looks like, you know, sort of a simple Boolean sort of figuratively sort of circuit like this, where the A, the port, can be set to 0 or 1s, the DDR can be set to 1s or 0s, and what do you see at the pin? Well, there are different outputs here. Well, if you put this to 1, then yeah, it means that you really use this port as output. So if I see a 0 here, I see a high out 0. I see a 1 here, I see a high out 1. If I use this, however, as an input, and I put for the port a 0 or a 1, I should not see anything at the pin, right? Because I don't use the port to reflect something toward that pin. Because you use it as an input. It's not connected, you would say. But effectively, there are two cases. One is, you know, if I have this particular case, wait a minute, where are we? This particular case, port A is set to 1, so I'm actually setting that to 1. And the register is 0, meaning that I'm only interested in inputs. I'm not really interested in making this an output at all. But this will eliminate static effects and noise and so forth, and it will be and it effectively activates the pull-up resistor and makes reading of the pin now more reliable. Now, this other option over here, where the port A is set to 0, is good for creating high impedance if you do not want to use the pin to have any current at all. So that's kind of interesting too. Alright, so that's a little bit of detail, but now that we've talked a little bit about the mechanisms, the mechanism behind these registers, let's now talk about the switch. So what we want to do is we want to create a debound state machine. So a switch is being pushed, it may then go in the air, right? And it's somewhat unreliable to what you will see coming from that particular switch to the input pin on your microcontroller unit. Well, what we want to do is we would love to create some maybe software mechanism, that's the option that we'll be discussing, so that we can sort of filter out that type of noise. So just now I was explaining to you in the tri-state buffer that putting a 1 on the port for an input pin will sort of create this pull-up register, and it's a hardware mechanism to filtering out noise. But right now we have a switch somewhere out there, and we're looking at what it gives me as an input, and I want to find out, can I do something else to be able to filter out noise? And I can by actually creating what we call a debound state machine. Alright, so if you don't do any debouncing in software, then it looks like something like this. So say we create a variable, push flag no debounce, so meaning that we do not implement debouncing at all, and we want to just record in this particular variable whether I have a button push or not. Well, so I have this particular task that I'm creating, which is effectively looking at this pin B, so the pin B register, and I'm looking at, well, let's interpret this. This is hexadecimal 0x, the 8 stands for 0, 1, 0, 0, right? The 0 stands for 0, 0, 0, 0. So I see here a 0, 1 and all zeros, so that 1 indicates the 7th bit. That 7th bit, B7, is now being read out if I have this statement. I invert pin B, so that means that that I will actually swap every single bit to its complementary value, right? And that means that this particular statement holds true, right, if that B7th bit had a 0 at that particular position in the pin B register, because after swapping it would be equal to 1, right? So 1 and 1 would be 1, and that would then be a non-zero value, which will trigger this if statement, and then will set, yes, I have pushed the button. Because when I push the button, then effectively I should see a low voltage coming in, which is a 0 interpretation. Now, if I have the negation of this, in other words, I see a high voltage or a 1, then in that particular case the push flag, then the switch was not pushed and put it to a 0. So this would be a very simple mechanism to program, but again, we would like to find out how we can make this more reliable. So what about a debound state machine? So have a look. So let's say we start in the state no push. Now, if we start with a no push, then let's check a button push. If the button did not push, or got pushed, then obviously we don't change the state, we stay in this state. But if it did get pushed, we may say maybe we have a push. We're not yet sure whether that is true, because maybe there's some noise in this, maybe I did not really push the switch and there was some vibration or whatever it was, and I didn't get certainty here. So what am I going to do? I'm now going to check the button push, and if that is true, then I know that the switch is likely to have been pushed. So at one moment, say right now, I'm checking, is there a button push? I think it is, but I'm not yet sure. A moment later I check again, and now I have effectively two samples of my pin that both say I have seen, say, this low voltage or a button push. Now, then I have confidence that yes, the switch was pushed, and I will go to the push state. Clearly, if the button is still pushed, then I will remain here, but if the button is not pushed anymore, well, not yet sure, I think it is, so I go to maybe push. And if I confirm it again, I will indeed go to the no push state. Now notice that I can, of course, go from here and then back to here, because maybe there is no confirmation, and I thought the button was not pushed, but on the contrary, when I now check for a button push, yes, the switch is pushed, so I'm not making any change to my pushed state at all. So it's a kind of a software filtering mechanism. And you may want to find out for yourself and think about what happens if we would, for example, increase the time beyond 30 milliseconds. 30 milliseconds is kind of a magic number for humans, because it has to do with our own reaction speeds, and we will have a lab that is going to measure the human reaction speeds at some point, and or maybe right now. And so this is actually quite interesting. So if the time is being increased, right, if it gets much longer, how reliable becomes this state machine? What happens if this time is decreased? So think about it yourself. You can always ask questions during lab. So now let's implement this debound state machine in this particular way. A natural way would, for example, be to, instead of using the enumerate struct that I once explained to you, you can also use the define mechanism to literally create these words to mean 1, 2, and 3, being integer values. So, but now I've introduced these words, and I can use those in my case analysis, in the cases that I'm looking at, no push, or maybe, or pushed. You can see that by defining this now my code becomes readable. And I'd like you to really be encouraged by implementing all those types of mechanisms to make your own code readable so that you understand what you do. So here we see switch. Well, depending on what the current push state is, if it's a no push, I will check whether I got a push, and maybe I will go to the maybe state if that's true, and otherwise I remain in a no push. This is the larger case, more code. In the maybe case, if I indeed see a push, well, then I go to the push state pushed, and I may introduce a push flag debounce equals 1 that I've not explained, and which we can do I use that? Oops. Well, anyway, I did not really explain that at all. So over here, if I have a yes over here, I want to also output something to the outside world in my program, right? So somewhere else there's another task that would like to know that the switch is indeed pushed. So I'm not only changing the state, like I'm convinced that I'm in the pushed state, but I also like to set a variable to 1. So that variable can be picked up by some other task, and maybe that push means, okay, I'm going to write something to the LCD screen or something like that. And similarly over here, if I am convinced that there's no push, then not only changing the state, but I also set this variable to 0. So that's what's happening over here. So the push flag is yes, and in this case no. So this is how this code works, and that's the kind of code that you will be implementing. Now, clearly we have now created a software debound state machine. SW stands for software, but depending on application, by the way, you can extend this final state machine, and I will ask you to do so at some occasions. It's kind of nice that if the push flag equals 1 is set, you may also want to do other stuff. Say increment a counter or something like that. Like I want to count the number of times I push a button. I could just extend the state machine with extra code right here in these particular two statements. So we can also use this state machine to create, for example, by means of hardware timers, I may be able to create kind of a stopwatch. And I can extend the final state machine again to make that happen, and we'll do that later on. Alright, the hardware debouncer. Now it turns out that your hardware debounce switch actually has a capacitor right here that of course helps to make sure that that bundling problem, that unreliability, is pretty much resolved by using a hardware debouncer. It's effectively, this filters out that noise for you already in the hardware. Now this costs you 1 extra capacitor, and sometimes you may want to save a few cents and then do what we just did in software, right? Create a software debouncer. Alright, so those are the pros and cons. Now, what I like you to do is to do software debouncing anyway, because it's a good thing for you to learn how to program that. Alright, so now we switch to the LCD screen, okay? So, I'd like to encourage you to have a look at that LCD data sheet. So we will look through a few tables here. And the first thing that we notice though is that, if you look at the Atmeca 328P mini user guide, which is not the LCD data sheet, right? That's a different data sheet. We notice that the MCU is being programmed through a few special pins. Now, some of you may have seen already that if you start reusing those pins for other purposes, that may actually give you some problems with your MCU. Now, here obviously we do not want to connect the LCD screen to those 4 pins. Why? Because if you look in this particular data sheet, you will notice that these 4 pins are used for special programming functionalities if you look through the data sheet. Now, if you would connect these right to the LCD screen, then if you do an LCD read operation, because it turns out you can also read from the LCD screen if you want to, then if that is then if a LCD read operation is interrupted, then the LCD is going to drive the bus from that moment onwards, and that means that the programmer cannot program the chip, the programmer chip that you have on your board. And you get a program failure, and even worse, the LCD must really be properly connected, otherwise the LCD does not acknowledge, and the program will hang forever if you would have used those pins. Those are scary pins, so make sure you don't you use them wisely. Alright, so the LCD library that we have constructed for you, you can find those again. They will be posted on the web page or PS or whatever, but you will now need to include this delay.h functionality. I told you I do not like to use it, but it has microseconds and milliseconds delay functionalities, and those are used in this library. Now I will explain to you why. So first of all, I like to stress though that later, next block, we will use interrupts to eliminate the delay millisecond functionality. We will keep the delay microsecond functionality because that is actually very hard to get by using interrupts. Now if you want to use this delay stuff, then you need to also make sure that the FCPU is defined to be equal to the right clock rate. Okay. Let's take a step back. Let's first explain the programming example that I'd like to explain to you right now. Suppose I want to put on my LCD screen literally the text number equal and then some variable that is 1, 2, 3, 4, 5, like a counter. And I have a little o that is going from one side to the from the left to the right and from the right to the left, and it keeps on going back and forth. That's what I like to display. Now the first thing that I'm going to talk about is how do you write number equal on your display. And by doing this I'm going to introduce a few new concepts. First, how do we store actually a string that looks like number equal? Well, we also have to add a special character, which is the /0 character, which is the all 0 byte. Why? That's just how C actually stores strings. So you have to end a string always with the all 0 byte. Okay. Now I would like to show you how you can store things in the program space. Now your processor actually uses what is called the Harvard architecture, where the RAM is used for data, while the flash space is used for the program, for the code. And what you could do though is, you can, because maybe you would like to store a lot of data, you could use some of that flash space for storing data. Now, you don't really need it in this application, but I'm going to teach this to you anyway, because I like you to experiment with it. You can actually use this particular special library, the program space library, and then you can define a constant of this particular type, and I'll just write it down like this, and this is a different way of writing character. So I teach you a lot of vocabulary here, and you can interchange this. You could have written char over here as well, but often in programs you will see this particular type and you would like to know what it means. So here it is. Then we're going to create this particular variable or the name for that constant, right? And this particular thing indicates to C, to the compiler, to look at the actual number of characters that you're going to store in the string that you're actually going to need to reserve for that constant in order to hold that chunk of characters. Then we have this keyword coming from this library over here that indicates to the compiler to store the string in the program memory and not in the RAM. So that's what we're doing over here. And now here we have our string that we talked about here. And again, we add with the all zero character because that's simply how we end strings. So I've explained to you a bunch of things here in this particular construct, a different way of writing the type character. It's right here. We have program memory that you can use for storage, and the string should also always be ended with the all zero byte. Alright, so this is what we're going to use, and what are we going to do? So we need a lot of includes, the usual stuff, std lib, stdio, but now also the program space. We add some other stuffs. Delay is needed for our own library that is down there, and so forth. Okay, so we're going to define this particular constant. We do one that has the string lcd initialized, and the other one has the string number equal. Now this is a variable, also of the type character, right? It's an array with 17 characters. The last one is to hold the all zero string, and the other 16 characters we can fill with whatever we want. And the idea is that we are going to write a whole string coded up in this particular array, all immediately we're going to send it through our library that we use here. There's a functionality that can help you to just transmit that whole string over to your MCU, to your LCD screen. We will have another variable, the count, that I like to put on the first line of my LCD screen, and we have a position of where I am with my little o, and the direction. Do I go to the left or do I go to the right? Now, why, by the way, do we use 17? Because the LCD that you have can print exactly 16 characters on a single line. Alright, so what are we going to do here? So first, and again, I'll teach you something new.